In this video, we are going to be deriving the equation for electrical potential energy using step-by-step explanations and a few examples to help clarify the process. However, before we jump into that, let's review an example with similar steps you might have seen before, calculating the gravitational potential energy of a system consisting of a box and Earth. In order to raise the box at constant speed, someone needs to exert an upwards force on the box equal in magnitude to the force exerted by the Earth. In this case, we can take someone's hand and hold the box up in this way. The person then raises the box through a vertical displacement, delta y, doing work on the box and adding to the gravitational potential energy of the system. We can build an equation from this bar chart that represents this event mathematically, with the work done on the box being added to our initial gravitational potential energy, totaling to the final gravitational potential energy we see on the right. We can rearrange this work energy equation so that the change in our gravitational potential energy is equal to the work done by the person lifting the box, with work being the scalar product of the force exerted on the object and the object's vertical displacement. Since these two vectors point in the same direction, the angle between them is 0, cosine of 0 is 1, leaving us with this equation. If we compare the right side and the left side of the equation, we can conclude that since both sides include some final value minus some initial value, the equation for our gravitational potential energy must be mgy. Let's look at this example in a little more detail. Imagine we repeat this process but break it down into smaller steps. In this case, we move the box up only a small displacement delta y1 corresponding to the area of a small rectangle under the force versus position graph. We can calculate the work done on the box through the same method as before, only with the smaller displacement now rather than the total delta y. We can repeat this smaller step again for another displacement, delta y2, adding another contribution to the total work done. We can then repeat this for another step, continuing with the same process, and one final step finishing at the same final position as before. We add these steps together and move the equation around, simplifying and combining like terms to come to the same final equation as we had previously. While these steps may seem a bit excessive, the key thing we learned from this example is that the work done by the person lifting the box, or work in general, is equivalent to the area under the force versus position graph. Knowing this now, let's discuss how we can apply these concepts to our electrical potential energy and analyze what's happening as we move two charged objects closer together. We can start by placing a charged object on a stationary point and another charged object on a cart, with a person pushing the cart to the left. Here we can see as the two objects get closer together, the person is doing positive work on the system, adding to the overall electrical potential energy we see in the end. Like before with the box, we can set up a work energy equation to represent this event, with the initial electrical potential energy and the extra work added to the system summing to give us our final electrical potential energy. Moving this equation around, we find almost the exact same equation as before, and like before, if we can solve for the work done on the system, we can derive an equation for our electrical potential energy. Like before, we can derive the work done on the system from the force the external source, in this case our person, is exerting on the object in question. As the object moves along the path, our person applies a force to keep the object steady, like before with the box. However, here we find the key difference between this example and the previous one. Our person is exerting a force equal in magnitude but opposite in direction to the repelling force between the two charged objects, which we can calculate using Coulomb's law. However, unlike the box example from before, our force is no longer constant. We can visualize this a bit more clearly if we separate this action into smaller steps like before. Here we see for this initial step, the force our person must apply is relatively small. However, towards the end of the path, with the same length and step, the force our person must apply is much greater in magnitude. In addition, another unique aspect to this example is the way the charges affect the force and the work we do on the system. Here we have two charged objects that are attracted to each other rather than repelled. This not only changes the sign of our potential energy, now giving us a negative value, but changes the direction of the force our person needs to exert to keep the charge at a constant velocity. As we discussed previously, the value of our work depends on the angle between the force applied and the direction of the displacement. Here, the angle between the two vectors is 180 degrees rather than 0, giving us a negative 1 from the cosine, which will carry through the solution, flipping the sign for the work. We can break this down like we did before with the box. Here we see the repelling forces between the charges, but what we really need to focus on is the external force exerted by our person, equal and opposite as mentioned previously. We start with some initial electrical potential energy and the force exerted, but because the force is no longer constant, we have to split it up into smaller steps to calculate the work done on the system. For each small step, we can approximate the work done on the system using the same method as before, finding the length of the step, delta r in this case, and finding the corresponding force exerted at that point. We repeat this process for every step, multiplying our force by the distance we traveled, with the force growing greater and greater as the objects get closer and closer. Unlike before, however, the force exerted changes from point to point, meaning we can't just rearrange the equation as we did before with the gravitational potential energy. In addition, this is a very rough approximation to begin with, The rectangles we're making with the graph don't quite cover everything under the curve, and no matter how we move them, they either overshoot or undershoot the true value we're looking for. In order to get a more accurate value for our work, what we can do is shrink the size of our delta r or delta y steps to better cover the area under our curve. We can repeat this process again, making the rectangles thinner and thinner until we ultimately come to a point where we're making the steps so small that they're practically infinitesimal. At that point, we're no longer just adding up a bunch of individual chunks, we're smoothly accumulating contributions from every tiny bit of displacement. This method may seem familiar if you've dealt with Riemann sums before in your calculus class, as this limit as we shrink the sums is what defines an integral. What this means is that rather than writing a sum like we've been doing, we can now write our work as an integral over the r values, or whatever value for position we're using, giving us the exact area under our force versus position graph. Using this method, we can finally start deriving an equation for electrical potential energy, as we can work with equations to integrate and solve analytically. So, let's finally calculate the amount of work done to move our two charged objects closer together. The first fact that we can use is that the force exerted by the person is always opposite to the force that object 1 exerts on object 2. This is true if we have like charges, as seen here with the person pushing in the negative direction while F1 and 2 is positive, or if the charges have the opposite sign, as seen here with the person pushing in the positive direction while F1 on 2 is negative. What this means is that we can replace F person on 2 with the negative F1 on 2 in the work integral. We know that negative F1 on 2 is just the Coulomb force equation, and additionally the dr vector is just the scalar value of dr times r hat. Substituting these into the work integral, we end up with the following expression. Rearranging a little bit, we can put the scalar product of the two r hats together and extract the rest of the scalar quantities left in the equation. Now, let's take a look at some of the signs of the various terms in this equation and check that A, they make sense, and B, are consistent with what we intuitively expect. First off, there's an overall minus sign in front of the equation that we get from what we just explained. Next, let's consider the signs of the charges, either positive or negative, of which there are 4 combinations. In the case of like charges, we can have plus plus or minus minus, and in the case of opposite charges, we can have plus minus or minus plus. Looking at our dr, this value will be negative due to the fact that the integral from r initial to r final moves from a larger value to a smaller value. Finally, r hat dot r hat is just equal to plus 1, since they are both unit vectors pointing in the same direction. While everything is checking out so far, we can simplify this information a bit by condensing down the values for the charges. If the charges are the same, then their product will always be positive, and if the charges are opposite in sign, their product will always be negative. Continuing on, we can figure out the overall sign of the work depending on our cases. Minus times plus gives us an overall plus sign consistent with what we've discussed before. Minus times plus gives us an overall minus sign for the work, also consistent with what we intuitively understand. It takes positive work to bring like charged objects closer together, while it takes negative work to bring oppositely charged objects closer together. Rearranging this equation and putting constants out front, the integral of negative dr over r squared is equal to positive 1 over r, with the bounds of the integration ranging from r initial to r final. We already established that the change in electrical potential energy of the system is equal to the amount of work done by the person on the system. Therefore, we conclude that UQ final must be KQ1, Q2 over R final, and UQ initial must be those same quantities over R initial. Just like with the gravitational potential energy example, since we have an initial and final on both sides of the equation, we can conclude that our final equation must be KQ1, Q2 over R.